All right, folks, this is a quick video on drawing forces. So this is step one in a longer slide deck, but I'm trying to break it down. Um, so really super important. You've got to have the right force diagram because all of your other analysis is based on that force diagram. Okay, so we're gonna go through and give you a set of hints to know how do you know which forces are acting and what direction are they acting. Okay, so you're going to use your acronym. We must never forget this to draw all your forces. So force number one is weight. Every single object has weight because all the experiments we're going to be doing is on Earth and does a vector pointing towards the center of the Earth. Um, Many engineering textbooks will have you draw all the forces at a single dot. And just to be clear, like how the forces are originating. And so pointing straight down, and this is the force of the weight. Okay, so super easy, always there. The formula for weight is mg. Okay, so that is force number one. Force number two is mechanical. And 99% of the time, it's already on the diagram for you because I need to tell you there's a fan, and the fan is pushing with, in the lab, I think it was like 0.215 newtons, and the direction. Super quick. People always get confused about, is this the way the fan is blowing or is that the force of the fan? Since this is a force diagram, I will be drawing the force of the fan, which means the air molecules are going in this direction by Newton's third law, which we haven't learned yet, pushing the object in the other direction. So I will always tell you the force of the fan, okay, or a jetpack or a person. So again, most of the time you got to be told that because you there's not a specific rule. But it's just nice to be on the lookout for that. Okay. And then normal force. This one can be tricky. In many ways, it's tricky because most of the time it's what I call boring. So what you do is you look for surfaces. How many surfaces do I have in contact? The person has a normal force on each of their feet, but reason we call this a free body diagram is we are freeing the box from everything that's going on and we're focusing on the box. And the box is touching one surface. And what does the surface do? The surface flexes and is stressed out and pushes away. Not always up, but away. So we have the force of the normal caused by the surface below flexing and pushing up. But if it was a fan cart and the fan pushes that cart into the wall, then that fan cart is touching two surfaces. So you have the force of the normal, and you need subscripts because there's two of them. So sorry, my handwriting. This is the force of the normal from the floor, and then you have the force of the normal from the wall. Or you can call them FN1, FN2, whatever, but they cannot be the same because you have two different ones. And this purple one isn't necessarily that big. I was just trying to, make it clear. So two surfaces, two normals. Normals are not up, they push away from the surface. All right, moving on. So we got friction. There's two types of friction. Sliding friction is what you think it is. It's going to oppose the velocity vector and it is parallel to the surface. So here's your surface. If you imagine, and we're going to talk about this separately, this is just a quick review of all the forces. Here's all the nooks and crannies on the floor. Here's all the nooks and crannies in the box. And they're going to bump up against each other and you have the force of friction opposite the velocity vector. It's always opposite the velocity vector because it's the motion of the box that's making the nooks and crannies run into each other. Okay. Do not draw the velocity vector on the force diagram because this is just identifying the forces, and velocity is not a force. It is a vector, it has direction, but put it off to the side so that you know, oh, friction is going to be opposite that, but otherwise, you don't want to add that in your sum of the forces. You don't want to accidentally add the velocity. I've seen that on tests before, right? And you can't mix and match newtons and meters per second. Okay, so sliding friction is going to be pretty much what you think it is. Opposite the motion, making something slow down. Static friction is really tricky, so we are going to spend a day on static friction. Not going to talk about it too much now, but the rule is it's parallel to the surface and it's opposite the tendency to move. So this is like if you've got a really, really, really heavy box and you're like, it's not moving, it's not moving, then we call that static friction because static for stationary. And I wish there was a different name for it because we think of friction as two surfaces sliding over each other. I think we should call this like the interlocking force or the Velcro force. These nooks and crannies are really just locked in, and that's why this box can't move. It's because it's really a whole bunch of normal forces between the dark purple and the light purple surfaces. Okay, so which way does the box, quote, what would it move, which way would it move without friction? It would move to the right. So which way is static friction? It is opposite that because by trying to move to the right, these nooks and crannies are interacting and you have static friction. Okay, and again, we're going to talk more about that because that was tricky. And then the last one is, ironically, the very first force that we did, just because of the acronym, we must never forget this. And that's pretty straightforward. You want to look for ropes. And the rule is that the rope molecules are stressed and the tension always points towards the center of the rope. So you have tension pulling the box towards the center, so a little bit over and a little bit up. But you also have tension pulling the person a little bit back and a little bit down. So there's always two tensions, one on either end. Remember, we did the demo with holding the rubber band in your thumbs. But because we're freeing the box or focusing on the box, you're only always going to care at this point about one of those two tensions. Okay, so the rule is find the center, draw the tension. If you would like to draw the tension on the other end of the rope, because it's there, but it's acting on the person, by all means do that, but know that when you're only analyzing the box, so you're only going to focus on the forces on the box. All right, so that was a quick just shorthand to review. How do you know what should go in a force diagram? Everything that you're going to draw in the force diagram is in this acronym. Again, sometimes you have to be told about mechanical, sometimes you're told about air resistance, but for the most part, this is what's going to get you set up. And once you got your force diagram set up, you are halfway there. Thanks for listening.